All right. It's probably not too common to give a talk as one of the organizers, but partly this meeting is to revisit Peter Greenberg's work. Well, I never met him. I guess I was a very young boy when he passed away, very young, apparently. But for those of you who actually knew him, please say something about him. He has done interesting work on piecewise linear stuff, and it's related to both group theory, maybe dynamics, and also foliation theory. And the audience is kind of diverse, so I'm going to start from basics. This could be actually the prerequisite to Takashi's talk, so we can switch our talks now. Okay, so my first talk is going to just motivate why we care about this classifying space that we call B gamma. And the second talk will be about Greenberg's work on B gamma 1 PL. And the third talk will be about B gamma 2 PL. Okay, that's the plan. So let me start with the definition of foliations. When we have a manifold, say M, this is M, and when we want to talk about any kind of structures, maybe geometric structures on M, we have some model space, maybe X or something. So X is our model for geometry. And then we think about some symmetry of this space. It could be maybe if X has some metric, it could be the isometry. It could be pseudogroup on X instead of the subgroup of the diffeomorphism group. And then we're going to cover the manifold M by open sets, maybe U alpha, U beta, and maps to X, say phi alpha, phi beta. And then normally, maybe around points in the intersection, we are going to have transition functions, say phi alpha, maybe times some transition functions. Alpha beta is phi beta on X. And this transition function is what matters when we talk about geometry. If, for example, you think about maybe geometry on three manifolds, this space X is going to be some homogeneous space, and your transition functions are not just local diffeomorphisms, they have this analytic extension property that they come from global map on X. Okay? And for foliations, so if you have foliations, you can also do this. So, locally, not like this. So codimension K foliations. In particular, it's modeled by, if this is M, maybe this is Rn. And then locally, you have foliations by codimension K hyperplanes, and then in that case, so in this example, your transition functions, so gamma beta alpha, are given by functions like f of xy, g of y, where xy is in Rn minus k times Rk. Okay, so your transition functions are given by some local diffeomorphism of Rn, whose first n minus k coordinates, you don't have any condition on it, and the last one are going to depend on the last n minus k on the last k coordinates. Okay? So this gives you the definition of codimension k foliations, depending on also whether you put any restriction on the regularity of these functions. You know, one way to get foliations on a manifold is if you have two manifolds, say M of dimension n and a map to a manifold of dimension k. If you have a smooth map that satisfies, that is submersion, say. So suppose that F is a submersion. Then the inverse of any point, this gives a codimension k foliation on F. Sure. Okay, that's actually the prototype of actually building foliations. This is somehow a global construction, but you can do these things locally and glue them together. And so that's going to be the way we are going to think about classifying foliations. So, so if you have a cover, so let's U alpha be a cover for M. And if you have, say, functions on each of these things that are submersion, so let's say you have F alpha and say to RK, let's say submersion, that locally gives you codimension k foliation, then again, when you map it to RK, if this is the intersection X and this is maybe phi alpha, and this is phi beta, this is going to be, you know, some open set in RK and some open set, some other open set, the image of phi alpha and beta, and then this is maybe phi beta X. Or I said F alpha. Maybe I should say phi alpha. No, F alpha is better. Let me say F then. And then F alpha X. Then you have some local diffeomorphism of RK sending one to the other. Say this is alpha beta. So you say F beta is alpha beta F alpha near F alpha X. Okay, and these transition functions in this case that I'm mapping to RK, they satisfy some co-cycle formula. You know, the usual thing that if you have X in the intersection of three open sets, say U alpha, U beta, maybe U gamma, then you have the usual things that gamma of alpha, maybe I shouldn't say gamma, say theta. Theta is gamma alpha beta, gamma beta theta. Okay, again, near F alpha X, in the neighborhood of F alpha X. Okay, so when you have this, then that means that you can locally pull back points on RK, get codimension K foliation, and glue, and get a codimension K foliation on M. And that's the data that we consider. So, so we consider this cover U alpha, F alpha, and these transition functions. Satisfying co-cycle formula. This gives you foliation, but as we just said, if you want to classify and somehow build some universal object, you want to pull back along any map, and you may not have this transversality condition like submersion. And for that, you relax this condition. Instead of saying you have local submersions, you just say you have maps. Okay? So we drop this submersion condition for F alpha, and we consider such triples. Okay? So forget about F alpha being submersions. And then in that case, we say definition. We say this is a Haefliger structure on M. Okay, I should say how we think about equivalent Haefliger structures. We want to classify such triples up to concordance. So
there's no conditions at all on the Fs?
On what?
On the Fs you have no conditions?
It's just depending on the type of the foliation. If you, for example, want to think about on F there is no condition. That's right. So these things are going to be the transition functions are going to give you the transverse structure of the Haefliger. It could be, say, CR diffeomorphisms, local diffeomorphisms, or PL, or anything.
Am I allowed to always take the F to be constant, maybe to 0, and then the gammas to be identity? Is that a legal Haefliger structure? Okay.
Yep. So definition, we say, so let me call this triple, let's say H. Then we say H1 and H2 are concordant if there exists H on M cross 0, 1 such that the restriction on M cross 0 is H1, and on the other end is H1. Oh, H0. So H1, H2 then. Okay, so what we are going to care about is the Haefliger structures up to concordance. But you see, this is a more relaxed structure on a manifold than foliations. We should say why it's going to be useful. So that's part of the motivation for these spaces. Okay, so any questions so far? What is it?
Continuous.
F is continuous, yes.
No.
But no.
You have 3 boards.
Do I?
Yes.
Yes.
Oh.
Doesn't that big white space up there? That's suggested.
Oh, I didn't know that. Good. Okay. So where are we? Okay. So now let me define the Haefliger groupoid. So definition. Haefliger groupoid. So let me first just think about the smooth category to start with. So gamma k is a topological category. In fact, it's a groupoid in the following sense. So we have the space of objects, which is just Rk. So points in Rk are the objects, and morphisms between 2 points is defined to be the germs of local diffeomorphisms sending x to y. Oops. So you have the usual topology on Rk, the set of points, and you have the so-called sheaf topology on the set of germs. And this is a category that we can take the classifying space of it. So for those of you, I know this is a again, diverse audience, so I should say what I mean by the classifying space. So the nerve of the category.
Can you say a bit more about this sheaf topology?
Yes. I'm going to say it after I say the nerve. So the nerve of the category, it's a simplicial space here. So you say n0 gamma k, it's just the objects, n1 gamma k is the morphism space, n2 gamma k is a pair of composable morphisms, and so on. Okay? In this case, you get a simplicial space. So this is your space of vertices, space of edges, space of triangles, and so on. And you can realize it. You can geometrically realize. And so the B gamma k is the realization, or the so-called fat realization of this nerve. This is, you know, the Eastern union of these simplices, space of simple.
N3 gamma KB, just triples of pairwise composable.
Yes, as a sequence. Yes, not pairwise, as a sequence.
As sequence.
Yes. So this is going to be I.
They'll be ordered.
Yes, tuples of composable things. So like n3 gamma k is the set or space of, say, you know, f0, f1, f2 that you can compose f0, f1, f2 makes sense. Times the I-dimensional simplex divided by, you know, the phase relations. Okay, so this is this space that is going to matter for us for the mini course. I'm going to motivate that in this talk, but going back to the topology on these things, so maybe as a remark. So what do I mean by the sheaf topology? So if you have, so I'm going to tell you one open set in the space of morphisms. So suppose you have some f from u to v. This is a local diffeo, say in Rk. Then you consider the set of the stock of f at different points in U. So I'm going to denote that by so the union of f of say little u, u in U. This is germ of f at U. This is an open set. This is an open neighborhood. Is a neighborhood of f of x, x in U. Okay, so if you have a germ, it's given by some local diffeomorphism, and if you look at the stock of this local diffeomorphism at different points in that open set, it's going to give you a bunch of germs, and those germs are giving you a neighborhood of the germ you started with. Okay. All right. So this is some.
The morphism space is some kind of super crazy non-Hausdorff, non-second countable.
That's right. That's right. It is still a k-dimensional manifold, but it's non-Hausdorff. Meaning that, so going back to the Haefliger groupoid, you see if you look at the space of morphisms, you have two maps, say source and target, to space of objects, and these are étale maps, meaning that these are local diffeomorphisms, and this is Rk. Okay. So this object locally looks like Rk, but it's very non-Hausdorff. Okay, so I have to motivate this space for you. So here are a few theorems that people proved in early days of foliations.
Sorry, this is the topology on N1. Then you extend it to B.
Then similarly, you get a topology on composable ones. Yes. Yeah. So the first theorem was, of course, due to Haefliger. Yes.
And then you're saying that okay, for N1, this is a k-dimensional manifold, and when you go up, the dimension increases, right?
Still is k-dimensional. Yes.
Because of the sheaf
You're taking a fiber product of a k-dimensional thing over a k-dimensional base.
Yes, yes. Okay, so the first theorem is actually kind of abstract, and this is true for many geometric structures, not these things, that the homotopy classes of maps from, say, manifold to B gamma k, this is pi 0, the homotopy classes, this is in bijection with the concordance class, class of gamma k structures on F. Okay, so in a way, it's a classifying space for these kind of structures. That's one. But we started thinking about foliations, and then we relaxed the condition. We have to say why this is going to be useful, and that's one of the foundational theorems in this topic. I probably shouldn't put the foundational theorem in the corner of a board. Let me change the board then. Okay, and so the foundational theorems goes back to Gromov and Thurston that tells you that if you start with gamma k structure, you can actually regularize them to a genuine foliation, and that makes these spaces interesting. So basically, if you're interested in classification of foliations, it translates into the homotopy type of these B gamma spaces. That makes why we care about the homotopy type. So this is a theorem of Thurston. So let me say it in this way. If you start with the manifold M, say n dimensional, this manifold has a tangent bundle, and then you can think about tangent bundle as a map to BGLN R. This is the Grassmannian space that classifies n-dimensional vector bundles for you. And let's say this is given by the tangent bundle. If you have a foliation of codimension k, it splits your tangent bundle into two plane fields. One is tangent to the leaves, and the other is the normal to the leaves. So in the first reduction to algebraic topology, that means that you want to lift your map that classifies tangent bundle to something that splits the tangent bundle, meaning that BGL n minus k and BGLK. Okay, so that's just the plane field splitting. Then if you have a foliation, you also have a Haefliger structure. If you codimension k foliation, it also codimension k Haefliger structure, and that further lifts your tangential structure to BGLN minus k times B gamma k. Okay, and there's a natural map from B gamma k to BGL k. This is basically, if you think as a simplicial space, you see we think about gamma k as germs of diffeomorphism. You can take the derivative of a germ at the source and get a matrix, and this gives you a map from the space of objects here, which is germs, to a space of objects here, which is matrices. And you get a simplicial map this way that induces B gamma k to BGLK. Geometrically, it tells you that if you have a codimension k foliation, you can think about its normal bundle, or Haefliger structure, you can think about its normal bundle. Okay, so this map is already given if you have Haefliger structure gamma k, whose normal bundle sits in the tangent bundle of the manifold. Okay, so Thurston tells you that if you have this, so if you have this splitting, so if you have, so let's say the tangential structure, the lifting of tau m to BGLN minus k B gamma k is a.
We're just starting with the foliation of M, right? I mean, that's all we're starting with, nothing else?
No. I was saying that the starting point here is just gamma k structure that has this lifting property.
Oh, I see. Not a
Right. So the goal of the Thurston's theorem is to tell you if you have a Haefliger structure, when can you actually get a genuine foliation? And the theorem says that if you have this kind of splitting, then you can. Any kind of Haefliger structure that has this lifting property is a regularizable.
And that's necessary?
And that's necessary, yes. Meaning that, up to concordance, you can change your Haefliger structure to get a genuine foliation. Okay? And here M could be, open or closed of any codimension. So that's.
But given a brief debate we had a while ago, this is actually, it seems like magic, except that you have the Tony Phillips theory about submersions, repeating it, right?
Right.
That if you have a submersion, if you have a map that looks like it might be a submersion, is a submersion.
Right.
And that what Thurston did was jazz that up.
It's even more than that. I think if you just say Phillips, it's like M is open in a submersion theorem of Phillips.
Yeah.
But really the contribution of Thurston was when M is actually compact manifold. That makes it a really hard theorem. If M is open, it's just the jazzed up version of Phillips, as you said.
But that helps understand how we might have thought of this.
Right. I mean, that was the starting point, yes. In particular, you have this version of Phillips on, on a neighborhood of n-1 skeleton of the manifold, and somehow you want to extend it to the top cell, and that's hard. Okay, but that's a foundational theorem that Thurston proved that somehow translates existence and uniqueness up to concordance of foliations into homotopy theory. Okay, so now if you like homotopy theory, it makes studying this space interesting. And how can we study the homotopy type of this space if you're interested in this problem? Yes?
I think the sentence is not complete. You were saying if the lift splits,
The lifting of the tangent, the classifying map for the tangent bundle.
Was the case.
Yes.
What's the sentence?
The sentence is any Haefliger structure, maybe I should say it this way, any Haefliger structure whose tau m has a lifting sorry, yes. Okay, so how did Thurston and Haefliger study B gamma? So this goes through, maybe I should also say math. Yes?
Question. Sorry, I have another question.
Yes?
So Haefliger's theorem says the Haefliger structure gives you a map to B gamma k. So does this lift have to be that map on that factor?
Yes.
So it has to be that map, and then the content is that you're also lifting it not just to that factor, but to the
Yes.
to the product.
Yes. Maybe another way of saying it is when you have a Haefliger structure of codimension k, it gives you a normal bundle, k-dimensional, and if that k-dimensional vector bundle embeds into the tangent bundle of your manifold, then you can regularize your Haefliger structure. Welcome. Okay, I should say maybe Thurston, Haefliger, and Mather. So this is the relation between B gamma and diffeomorphism group. So let me say by way of example. So example. So suppose you have a diffeomorphism of the interval. Say compactly supported diffeomorphism of the interval. Okay? You can, from this, you can build a foliation on a cylinder. How? You see, you have the horizontal foliation on square, and then you just glue the two ends by your diffeomorphism. You get something on the cylinder that is trivial near the boundary. And then from this, if you collapse the two ends, you get sphere and something that is singular at the ends, and then given by some sort of suspension near the poles. Okay? It's not hard to see. This is, although it's a singular foliation, it's given by Haefliger structure. It's a gamma 1 oriented Haefliger structure. And this is Haefliger structure on S2. So from a diffeomorphism, you get some element in pi 2 of B gamma 1. In fact, because it's co-oriented, it's a little bit better than that. So let me actually define space for you. Okay, maybe a little bit of digression just to define some space. So remember, if we consider B gamma k, say in the case of smooth, you have a map to B GLK R that classifies the tangent bundle. So let's call this map nu. Then say the homotopy fiber or the fiber of this map is sometimes denoted by B gamma k bar. This space also shows up in Takashi's talk this morning. And because in the case of B gamma 1, the Haefliger structure is co-oriented, in fact, so going back to the example, you start with phi as a diffeomorphism group of the interval, and then you get a map in, you get a class in pi 2 of B gamma 1 bar. Okay? It's not hard to show that B gamma 1 bar is simply connected. That's some easy geometric argument. And then this map factors through the commutator of this group. So then you get a map from H1, the first homology, or the commutator, or the group mod its commutator of diff of the interval to H2 of B gamma 1 bar. Okay? And the theorem, so the first thing I guess historically was observed was that this map is isomorphism. Okay? So theorem of Mather. It's more general than this, but this was the first instance that going from a diffeomorphism group as an abstract group to this space that we are interested in gives you some understanding of the next homology group or the next homotopy group that you want to study. It was easy to say that the pi1 is 0, but it was hard to say what pi2 is. And then you get this isomorphism, and yes, so a few things are in order. So in fact, this theorem is more general, I should say. So there is a theorem of Mather is not just about H1. It tells you that there is a map from the classifying space of the group, say compactly supported. I can just consider compactly supported diffeomorphism of R instead of interval made discrete. This is the group made discrete. This is the classifying space of the group as an abstract group. It's defined similar to the realization of the nerve of a category. This is a category with one object with groups as morphisms. There is a map similar to this suspension map that goes from this space to the loop of B gamma 1. That is homology isomorphism. This is the space of loops. Okay, so when you take H1 of this classifying space is H1 of the group, and then H1 of the loop of this thing is going to be the H2 of that thing. So that's where the shifting comes from. But from the algebraic topology point of view, it gives you the delooping model, interesting delooping model for B diff of a interval. Okay. Any questions so far? Okay, so why do we care about this? I said that it helps us to understand the next homotopy group of B gamma that we are interested in, because it helps us classifying foliations. How does this help us understand H2? It just says H2 is H1 of this. Okay? But this is somehow something that I'm going to emphasize in this mini course, that there is a difference between somehow the smooth category and the PL. It's a bit surprising direction that Thurston used to study B gamma using diffeomorphism group, because from geometric perspective, these kind of theorems are called H-principle type theorems, meaning that you're interested in some geometric structure and you translate it into algebraic topology, and then the algebraic topology is easier, and then you say something about the geometric object. That's usually the correct direction. Here, you have the same type of theorem. You have something that is geometrically interesting because it's related to foliations. You have something that is purely algebraic topology. And then Thurston used this to study this, which is the unusual direction of using H-principle. And the way he used it was to remark. So Hermann again has a very important theorem saying that diffeomorphism group of S1 smooth is perfect. In fact, simple. Okay. And this is true for not just S1, but higher dimensional tori too. And this is very deep dynamical system theorem. Okay? But in the case of dimension 1, suppose that you know this, then when people knew that diffeomorphism group of S1 is a perfect group, they didn't know that the compactly supported diffeomorphism group of the interval was perfect group. It embeds into the circle. And if you have compactly supported diffeomorphism of the interval, and you look at the interval as a subspace of the circle, you can write it as a commutator of diffeomorphism of the circle, but can you write it as a commutator of things that are supported in that interval? That was already a non-trivial step that was made possible using this kind of theorems. Because there is a similar statement for B diff of a circle. B diff of the circle made discrete into, there is a map to B diff of the circle with a usual topology. It is not hard to see that diff of a circle is actually homotopy equivalent as a topological group to rotation. So this is homotopy equivalent to BS1. And then the fiber of this map is denoted by B diff of S1 bar. And then, again, a version of Mather says that there's a similar map from B diff S1 bar to a space of free loops into B gamma 1 bar. And then perfectness of diff of S1 tells you that H1 of this is 0. And then H1 of this, so this is homology isomorphism. And then H1 of this being 0 tells you that H1 of this is 0. And then the free loops, because this is simply connected, H1 of this is exactly H2 of B gamma 1 is going to be 0. And then you go back to here, and then you get H1 of the diff of the interval is 0. So you prove perfectness of the diffeomorphism of the interval using diffeomorphism of the circle by going back and forth of using Mather's theorem. OK. So one thing I should say, this theorem has been generalized massively by Thurston to any manifold. So there's a version by Thurston. So the theorem of Thurston the same sort of theorem is true for any manifold of any dimension. So I'm just going to say the type of statement without explaining much. So you can define B diff bar of M for any M similarly. And then there is a map to some sort of mapping space, which is the space of lifts of M to B GLN to B gamma N of the tangent bundle. And this is homology isomorphism. And Thurston used this theorem of Nariman to prove that the identity component of diffeomorphism of any manifold of any dimension is perfect, similar to what we just described for interval. You know it for one manifold, which is torus in that dimension. And then from that, you get for compactly supported diffeomorphisms of a ball. And then from balls, you go to any manifold again. OK, so that was the original proof of perfectness. OK, so that was a smooth category story. OK, in the remaining 10 minutes, let me just say a few things. about PL.
Is there any progress on calculating the cohomology of diff? I mean, you have this machine that turns it into topology, but the cohomology of diff of a manifold, has there been any other applications of it?
Well, you should talk to Sander. I mean, B diff of a manifold has been extensively studied, especially for disk recently.
Could you tell us about the discrete case?
I think he was asking about, are you asking about diff as a topological group, or?
I'm just talking about diff. Suppose we forget about Thurston,
Okay,
since he's gone.
okay.
And now we talk about diff, either discrete or normal. So you're saying Sander has, a lot of people have results for the standard diff, right?
Diff with the C infinity topology on it.
Right. Does that
Or bid.
translate into the discrete knowledge? Have they pushed any of that knowledge over to the discrete homology?
I mean, a little bit, I think.
I mean, I think you have, right?
I tried, yes.
Before you could, we just had the smooth category.
Right. I mean, I don't know how to summarize what can be done using what we know about B diff with the usual topology to B diff discrete, but you can combine. You see, Thurston tells you about the fiber of B diff discrete to B diff, and then there's a technology to understand B diff a little bit, so you can somehow combine these two things to say something about B diff discrete, I mean, that was part of what I did in my PhD. I can tell you more about that later.
Well, that's another talk. Okay.
Yes. Okay. About PL. So I think the story of PL is a little bit different. Because of Greenberg, we can directly study B gamma PL. And that makes it somehow the right direction for the application. So let me first say one theorem. So the theorem, this goes back to Epstein. Epstein has this influential paper that gives you some criteria that if a group is perfect and has some nice local to global property, then perfectness implies simplicity. This is one of the foundational papers. And then in the last chapter, he talks about PL, and he proves that the piecewise linear homomorphisms of S1 is a perfect group. In fact, it's a simple group. And the proof is actually somewhat elementary. It's nice. It's just maybe half a page or a page. Basically, because you can find a typical piecewise linear homomorphism of the interval, something that has only 3 singularities. And then every other piecewise linear homomorphism can be written as composition of these things. And then something that has only 3 singularities, you can just write a model for it and explicitly show it's a commutator. That's kind of the argument. And then you show it's perfect, and then using Epstein, you get simplicity. Simple means there is no non-trivial normal subgroup, okay? But he asked this question that let M be a PL manifold is piecewise linear homomorphism of M isotopic to identity. So this is isotopic to identity. a perfect group. Okay, this is still open question, somehow surprisingly open question. You might think that piecewise linear homomorphism might be simpler than diffeomorphism groups, but still open. So one thing that I did a few years ago was to show that piecewise linear homomorphisms of the surface, say surface, is a perfect group. And the proof is actually not constructive. It uses the philosophically right direction of the Mathers type statement. So the way that it goes is, so I guess remark, there is a version of Mather-Thurston theorem for PL. And then you use that and what Greenberg did for codimension 2 foliations to show that H1 of BPL is 0. So in fact, and use Greenberg so you see we have B gamma 2 now PL. Now everything that I said, you can say it for PL homomorphisms. You consider piecewise linear homomorphism of Rn, you consider germs of piecewise linear homomorphism. You can define these objects for piecewise linear also, okay? And then you have a map from B gamma 2 PL to say BGL2 R. This map is well defined up to homotopy, say. And then the fiber of this map, again, similar to what I said earlier, is denoted by B gamma 2 PL bar. So one thing that I proved that implies perfectness. So remember, perfectness in the case of the interval smooth was equivalent to saying that B gamma 1 is 2 connected. So similarly here, so the theorem that I proved using Greenberg's model was that B gamma 2 PL bar is in fact 4 connected. I mean, 3 connected is enough to prove perfectness, but in fact it's 4 connected. Okay. So these are some of the things that I'm going to talk about, but let me, maybe in the last minute, let me say something new in this direction. So something that showed up in Takashi's talk this morning was about B gamma 1 PL. So he mentioned that B gamma 1 PL bar, Greenberg showed that this has the interesting homotopy type, which is BR plus discrete joined with BR. This B of a discrete group for maybe geometric group theorists is like KG1 space. And then the God-Billon-Way invariant that Takashi defined gives you a map from pi 3 of B gamma 1 PL bar to in fact R tensor R over Q. Okay? So this is a connected space. This is a connected space. So the joint of these two spaces is going to be 2 connected. And then PL God-Billon-Way tells you that this space is not 3 connected because this map is non-trivial. So this is the, I guess, Takashi said it's GSGV, G Sergiesco, God-Billen-Way invariant. But one thing that I noticed recently, it's not been written down. In a paper, I proved that this is 4 connected, and I thought that it's not 5 connected, because there should be some version of God-Billen-Way to detect something non-trivial in the 5th homotopy group. So I was spending a lot of time to actually build that PL God-Billen-Way invariant for codimension 2. And recently, I just went back to Greenberg's model and tried to calculate what is pi 5. And in fact, so I think theorem to be is that pi 5 of B gamma 2 PL bar, say tensor Q, is 0. So there is no non-trivial God-Billen-Way invariant for codimension 2. And maybe as a last...
I mean, do you think there's torsion in there?
That I don't know. There might be. Maybe one comment I should say is that, you know, the area form that Takashi defined for codimension 1 thing, you have some function, you have some function from, say, S1 to the plane, and then you get a polygon. This function is, you know, is a discrete function. You can define the same sort of discrete function for codimension 2. Say you get a map from, say, S2 to R3. You get a bunch of points. You can also connect them, but there is no circular order to get a polyhedra. Somehow I thought that there might be a canonical way to get a volume of that polyhedra to get a co-cycle formula, but it turned out that you don't get anything interesting. Okay, that's enough for the first talk. Yes?
Is it, if you do the two-dimensional PL, homology, is it a limit of smooth objects? I mean, like the PL1, it's a limit of smooth objects, right?
I mean, I guess Takashi is more...
The polygon can be approximated by a smooth circle.
Right.
But is it, can you approximate your higher dimensional thing by smooth maps?
That I don't know. I don't know. This is something that I was hoping that Takashi is going to tell us more about. What he means by taking limits of smooth objects in the PL category and so on.
So the question then goes to Takashi.
Hopefully.
I don't know what they're going to mention too.
What?
You don't have all the things
All right.
Yeah.
The Thurston solve these Haefliger spaces for the PL space for subfields of real numbers. Is that theorem to be also true for any subfield of real numbers?
Not, you mean the connectivity statement?
Yeah.
That I don't know. That's an interesting question. So just maybe one comment. I mean, Sander is asking that, you know, the PL homeomorphism has this nice property that you can define interesting subgroups of it. You know, PL is piecewise linear, and then you can think about, you know, subfields of real numbers and think about slopes in those rings. For example, Thompson group is defined that way. We're going to hear a lot of talks about Thompson group. It's a subgroup of piecewise linear homomorphism of a line. And then you can think about what is the analog of this Haefliger for the Thompson group. And it's interesting that there's so this paper of G. Sergiesco, in which they defined piecewise linear God-Billen-Way, they they proved the following. Sergiesco. They proved that if you take the classifying space of a Thompson group F prime, which is the version that is the subgroup of the interval, goes to the loop of S3, and this is homology isomorphism. So the Haefliger space for the Thompson group with those interesting slopes is three-dimensional sphere, which is again two connected, similar to this joint. But that also, I think it's kind of a coincidence. I don't think it's true for any kind of subfields. Okay, well, I guess if there is no more question, see you in the afternoon. I forget what time.
1:30, I think.
1:30? Okay, 1:30.